So I think was summarizing some of the concepts that have come in the course, and I don't know if I'll really be able to cover everything, but I will sort of give my particular perspective on a lot of these things, and we'll be retreading on some places which have already been brought up, and hopefully deepening some of those intuitions that are important to have when you are doing these kinds of analysis or thinking about doing these kinds of analyses. So I have this title, What We Talk About When We Talk About Dynamics and Resting State Functional Connectivity, which is a very ponderous title. But really what I am interested in trying to talk about is what do these large-scale brain correlations reflect? Are they spurious signals? Are they statistical errors? Are they states? And we've heard bits and pieces about that over the course of the educational course today, and I'm going to touch on each one of these things. But I think it's also important first to go back again and remind ourselves of how we sort of got to the position we're in from understanding bold activity. So really, we've been using fMRI for several decades now to measure stimulus-evoked responses and measuring the bold activity in response to those stimuli. And we've been able to use that as a tool for measuring the brain's functional organization. So it's a very obvious example. Everybody knows, you can do a finger tapping task, and you'll see increased activity in the motor cortex relative to periods of rest. And this is, the archetypical task fMRI paradigm that is still being used very fruitfully. And you're able to then derive the brain's organization, or localize, I should say, particular brain activity related to the task of interest. What was quite remarkable was first observed back in 1995, though really not fully appreciated for quite a long time after that, is that there was spontaneous activity that's going on all the time while you're doing tasks, while you're actually just at rest. And this spontaneous activity is functionally organized as well. And so this is, again, actually from this same paper in 1995. You take two regions in the motor cortex, you derive their bold activity over time, and what you find is even while the subject is just laying at rest, not doing a motor task, not doing anything in particular other than staring at a crosshair, there is a strong correlation between these two parts of the brain in terms of the bold activity. This is what we call resting state functional connectivity. And one point to make is that these are low-frequency fluctuations, that the power of the correlation between brain areas is actually at relatively low frequencies, and the power goes up as you go to lower and lower frequencies. So we're talking tens of hundreds to 100 seconds approximately power where these things are. Okay, so you can go farther. We see this with motor cortex, but you can actually compare bold activity across the entire brain. And you can build what we've seen again and again today, these correlation matrices. Now we've got an extra area that's actually maybe not related to those two motor cortex areas, and so it doesn't have such a strong correlation. We can actually expand this out to the whole brain, and using a whole bunch of different methods that I'm not going to talk about at all because it's not relevant here, you can organize this correlated brain squared space and derive separable functional systems that can then be projected back onto the brain. And the enterprise of doing this has been developed over the last decade or so, where we've been able to establish fairly consistently across different methods relatively consistent patterns of separable functional networks. This is using network methods, using clustering methods. You can also get very similar patterns using ICA-type methods as well. And they give you very similar answers. And it's been very exciting and has led to huge amounts of research. And of course now, and the reason why you're all here, is does this consistent pattern that we've now seen, been able to establish across a lot of groups, how does this brain organization reflect brain organization at different temporal scales? And so what I have on here is a sort of spectrum of possibilities. On one end, we have moment-to-moment variability and brain states, and maybe as we go along, maybe changes over the course of the day, Do they reflect plasticity-related changes from extensive experience? And on the far end, there may be represent stable features that exist over the entire lifespan. And so there's really sort of two really opposed ways of thinking about what resting state functional connectivity actually represents. Does it represent stable features or features that change over short time scales? So just to let you guys know, the kind of data set that a lot of the stuff I'm going to be showing you is coming from, this is what we call the Midnight Scan Club data. This was a data set we've collected over the last few years, which is 10 subjects with 10 sessions of data. Most usefully in this context, we now have 5 hours of resting state data per subject, so there are 10 30-minute resting runs for each subject. In addition, there are 10 hours per subject of different tasks that we force people to do. And there are structural data as well as neuropsych batteries that have been done on these subjects. The description of the acquisition and sort of first-order analyses have been published. You can see more in this paper from last year. And I would like to point out that this data is publicly available. It is on Open Neuro and NeuroVault, so if you want to, you can download it and have at it. And it's, I think, a particularly interesting data set for exploring these kinds of questions. So that's the data we're going to be using. So getting back to this question of stability or long-term stability versus short-term changes, this now is representing an analysis looking at the similarity now of all of these sessions of data that we've collected. There are 10 subjects, 10 sessions, multiple tasks, and each dot in this correlation matrix is now represents a correlation matrix from that session. Okay, and so we're comparing the similarity of each session to each other, and the variables are subject and task. And what you can start to do from having this sort of complete spectrum of the data is say, how much of the variability in the network matrices that we're measuring are related to common features across subjects, how much are related to specific features of individual subjects, how much are related to being in a task state, how much are related to being in different sessions. Okay? So I'm not going to explain all of the ways this is derived, but basically this is giving you a sense of the relative contribution for these correlation matrices of those various factors. So about 35 to 40% of the similarity across these sessions or across these correlation matrices is explained by a group feature. That is, it's a common feature across all the subjects. About 35 to 40% of that, above and beyond, are stable individual features that exist in each subject. And then we have the remaining pieces of variability that are related to the task and are related to the session that they're in. Okay? So what we can say is that broadly, resting state networks are largely explained by common features and stable individual differences. And then the tasks and sessions do perturb these, but modestly, relatively speaking. So going back to this spectrum of the temporal scales, you can say there's a large component that's on this sort of the right side of the ledger here. But what we're talking about mostly today is the other side of the ledger. Now this is the sort of remaining 5, or I should say 10, 15% that was enumerated on that previous slide, that narrow piece. So what's going on there? So what are brain states? And I'm not going to be able to define this. I don't think there is a good compact English word that or set of words that will describe these, but we can give examples of what we mean. And some natural ones, especially ones we think of in terms of seconds to minute scale, are things like being in a goal-driven task or a particular stimulus context. There's also wake versus sleep, or different arousal stages would be considered different tasks, or excuse me, different states. And then things like mood changes. And I want to just, I guess, distinguish this kind of definition of states from what you might think of when you are actively processing a particular trial from a stimulus or having a fleeting thought where you're having input and output. These are broader scale features of what the brain can do. So this is actually getting back to a point that Raphael mentioned briefly which is how do we try to measure these kinds of things. So I'm again talking about evoked response, which is this traditional way, and now we're talking about let's use functional connectivity. And this is getting back to this question of what is the difference between these two kinds of measurements we're making. The evoked response is a first-order statistic. It's reflecting changes in the mean activity as we give a stimulus. It can be represented in brain space. That is, you can get a single image, and that will show the effect, the bold response. Functional connectivity is a second-order statistic. It's correlation or covariance, and it's represented in a squared space. It's the relationships between all of the regions in the brain. And I just point this out again just to sort of remind everybody that this may be, that these two things may be representing different kinds of mechanisms, may be relating to different things that are going on in the brain, and we may separate them, and we maybe should have different intuitions about how they work. So, so the question then is, can we see changes in resting state functional connectivity by imposing a task? And the answer, I think everybody would expect, is that yes, you can. Here's a sort of stark example. We have eyes open, eyes closed. Somebody, they're getting either full visual stimulus or none at all. And we're looking at the resting state connectivity pattern in somebody in those two different states. It actually might be a little difficult to see the difference and these two matrices are very highly correlated with each other, even though you have a fairly radical change in state. You can see a difference, of course, though, and it's localized mostly in the visual cortex. And does this work? I don't know. Yeah, there we go. Interestingly, also in a cross correlation with the somatomotor cortex. That's where the dominant differences are. So there are clear differences being induced by a task state, but they are subtle. We can go to a more subtle kind of task manipulation, where now we are putting somebody into different cognitive states by having different kinds of tasks. Here are the three different kinds of tasks where we have a semantic judgment, a mental rotation task, a coherent task. These are being compared again to a resting state, and we're looking at the difference in the correlation patterns between those two conditions. And again, you'll see this is the difference map along the bottom. Kind of interestingly, they actually are all relatively similar to each other, so there's sort of a common task effect of being in a task. And then there are effects that are specific to each one of the tasks. But again, these things are, if I were to show you the original correlation matrices without differences, they're all very highly correlated with each other. And these effects that you're seeing are significant but subtle. They fall into that 5% I was talking about before. So what if we don't have knowledge about the task that we've imposed? Can we detect ongoing signals? We kind of say we know that there are changing tasks or changing states going on. What's a good way to try to pull out that observation directly from the signal? So this is where it's helpful to introduce a measure that may capture this idea of state changes that may be related to resting state connectivity changes. So change in correlation, or the variance, is the variance of a second-order statistic. And that's related to the fourth moment of the statistic, which is the kurtosis. And so we can say then that the measurement of multivariate kurtosis, the multivariate fourth moment of our signals, gives us a measure, strictly speaking, of the non-Gaussianity of all of our signals. But if there is change if there is variance in correlation, it will pick up on that, though it may also pick up on other kinds of differences as well. So it's not as precise in some ways as you might like, as Vince was talking about earlier. So using this kind of measure, can we see transitions between rest and task? So we have ongoing signals of rest. We have ongoing signals where we have a rest and a task. And what happens to the kurtosis? You get an increase in the kurtosis when you have an epoch or a session that has both rest periods and task periods. So the multivariate kurtosis is capturing these subtle differences in functional connectivity of going between those two tasks, between task and rest. And that's what's depicted over here on the right. And they're all having greater kurtosis than our continuous rest state, which is in the blue there. So tasks can drive functional connectivity changes if we impose them. But what about within the resting state itself, where we don't have any kind of external imposition or experimental manipulation that we've done? So now things get a little trickier. As I said, we don't have an externally imposed perturbation. We don't have a particular model necessarily of what's going on. So we really need to worry about intrinsic variability of the data and sources of variability in the data that aren't of any interest to us, okay? So I'll go through some examples of those things. So as Raphael mentioned already earlier in the course, there's this important concept of sampling variability. This is just a sort of illustration of that. This is actually from Russ Poldrack's data, where he scanned himself over 100 times over more than a year. And this is measuring the similarity of each session's correlation to the mean correlation across time. What you see is there's sort of a range of similarity to that average. It varies over time. It's a variable estimate. We can actually, helpfully, because we have so much of this data, we can actually get a sense of how exactly, and this follows sort of from first principles of the statistics of sampling error, that how much data, or how does the amount of data you have affect your variability in your correlation, okay? So on the right now is a log-log scale of time we use to calculate the correlation value, and the y is the variance. And as we might expect, the area increases as the sample size decreases. So you get more variability with less data. You get less variability with more data. Okay, and it follows a pretty good rule there. So this has consequences in terms of how much data do we need to actually get a really good estimate. And so this is now a curve of, as you add more data, how similar do you get to your true connectivity? Where true connectivity is defined as, with Russ's data, where we had 1,400 minutes, we could set aside a huge amount of data and say this is the answer, and we're now comparing to that. And what you can see is there's a rapid increase up to about 30 minutes or so, and then it really starts to converge at about 100 minutes. And so this is why we really think that significant amounts of data are needed to get a precise estimate of the true correlation, or the true correlation matrix, I should say. Okay. So sliding windows, which we've talked about a number of times, capture or are subject to this issue of sampling variability. So this is just illustrating a sliding window. You're calculating the correlation value across time. Along the bottom is now the fluctuation in the correlation value as calculated by the window. And this is just to point out that that window size obviously is going to be affected by the sampling variability. So if you have a smaller window, that 100 seconds, you're going to get a wider range. And with the larger window, you're going to get a shorter range, just by the properties of sampling variability. Okay. So this is important to keep in mind when you're looking at these things. Okay, so this is, I think, one motivating reason why we really need to have a null model. We really need to understand or have some way of getting a sense of the level of sampling variability when we have that can be explained by a static or constant correlation matrix. So critically, we do need a null model of bold data that reproduces its static correlation and its frequency content. And I'll talk about the particular null model that we've used. There are many others that are actually better in some ways. So just to illustrate the idea here, we're now trying to build real bold data so that we can get a sense of what is the sampling variability of a simulation that has stationary characteristics of actual bold data, where we're now estimating those values from a full time series. So this along the bottom is an example of a time course. Then we have the power spectrum from that time course. We have the correlation matrix from the set of regions. And along the right is actually a kind of a sliding window observation for each one of the networks. So we start with, now to build the simulation, we start with random normal deviates. They have a flat power spectrum. They're independent, so they have no correlation or covariance, and we don't really see anything in the sliding windows. We can then enforce the stationary covariance from the real data. And you now have this data set is representing the static correlation that's in the real data, but it doesn't actually have that power spectrum yet. It doesn't have that 1 over F characteristic. But we can also impose that, the sort of calculated across the entire run from the real data, the bold spectrum, and impose that onto the simulation as well. And now what you see is, having done this, well, the properties that we've imposed in the simulation are stationary properties, but they are able to already generate interesting sliding window correlations or fluctuations in sliding windows. So this is just kind of fun. You can pick one and see which one you think is real, which one do you think is simulation. Is it done? Oh, no, not yet. Okay, it's a little long. It's 30 minutes run, so it's not going to take a whole 30 minutes. Okay, so who thinks the real one was on the right? On the right side? Who thinks it was on the left? Okay, a lot of abstainers. But most of you are wrong, okay? This is just illustrating that with a relatively basic null simulation, which has stationary characteristics, you can get all sorts of interesting fluctuations in correlation that are actually hard to distinguish from real data. As I mentioned before, we can go a step further and actually subject that kind of simulated matrix and the real data to these analyses where you're now capturing the states that exist, where you do this using like a k-means clustering, where you're taking all of your windowed time correlation matrices, doing k-means and separating it into presumed states. And we can do the same kind of maneuver on the real data. We can see real states. There are 7 states here. You can ask for more depending on how many you want to be interested in. But the simulation actually reproduces those as well. So it's possible that some of the things that are some of the state features that are being extracted are actually just a consequence of stationary normal multivariate data. As I said, there are other null models that actually approximate real data better than this simulation. So Raphael's paper nicely goes through a bunch of different kinds of null models and how to think about them. So the one I was just talking about is on the far right, and what's measured here is a KS statistic that's showing the similarity of the distribution of the signal from the simulation to the real data. And we actually can see is that phase randomized null data and multivariate autoregressive based null data of at least first order is actually doing it's more similar to real data than what I've been showing already. So what I think we can conclude from this is that spontaneous bold activity cannot be easily distinguished from a stationary normal multivariate process. And that is of some consequence, I think. So, are there states in resting state functional connectivity? Hard to say. So far, I haven't needed to invoke multiple states in order to get a reasonably good picture of resting state. But that's not completely true, actually. There are definitely things in the data that are of consequence and may look like states. Unfortunately, there's more we have to worry about as we start looking at those things. So now I want to have a display here of raw brain data and how to, I think, get a sense of how different kinds of artifacts affect your data. And this is a very helpful plot that we've found and I'll just explain quickly. Here along the side we have each row here represents a voxel from the gray matter. and there's no particular meaning to the sorting. It's just all the voxels. And then we have white matter voxels and CSF voxels. And then across here is the mean frame-wise displacement, which is just a measurement of movement from frame to frame. And so you can see there's these sort of little spikes of movement that occur when somebody shifts their head a little bit. And what you can hopefully also see is that during a motion spike, you get this very clear change in the gray matter plot, that there's an effect in the signal. So, as you might guess, motion of this type definitely introduces artifactual non-stationarity, or more explicitly, as measured here, more like artifactual non-Gaussianity. So plotted here is now the mean FD from all of those sessions. Each blue dot is a session, and the kurtosis, the multivariate kurtosis of that session. And what you can see is there's a fairly strong relationship between the mean FD in the session and the multivariate kurtosis in the session. Fortunately, you can do interpolation maneuvers and frame censoring where you remove those time points, and you'll get data that's much closer to the stationary simulation. So it now looks much more like the static simulation once you've done those maneuvers. There are, unfortunately, other things that can introduce dynamics in data or changes in the signal that may be not of interest. We've sort of known this back since at least 2006. Rasmus had an important paper on this. And here's another example showing this, up here we now have respiration traces and cardiac traces, heart traces, and fluctuations in the respiratory patterns that relate to the CO2 content, the partial pressure of CO2 in the brain. And we can actually see that when we have changes in the respiration rate, we get these kinds of long-term dips in the signal. And you can even experimentally do this, though this is just happening naturally. But you can experimentally do this and cause these kinds of dips in the data. This, of course, will also be a kind of dynamic feature that you would want to worry about. Again, fortunately, there are maneuvers to get rid of these kinds of signals, mainly, though we use global signal. There may be more targeted ways to do it if you have the right measurements. But this is just illustrating that if you do a global signal regression and the scrubbing, whereas here you can see all of these features that are both motion and respiration related. Down here, having done those manipulations, a lot of those features have been taken out. So that's an important thing to be thinking about. Okay, so those are all the things we've got to worry about that are artifactual changes in the bold signal. There are bona fide state changes, though. In resting state data. Subjects fall asleep during the resting state scans. So this is real, and people do it. And Tagliazucci, in an important paper, demonstrated that with concurrent EEG fMRI recording, they could show that individuals, as they were laying in the scanner, had a tendency over time more and more likely to be asleep. And they could confirm this because they actually had EEGs where we have good measures of what the difference between sleep and wake look like. While we didn't use their bold data or their resting data to derive this, we used their data set to come up with a kind of sleep index that was describing being in a more asleep or more aroused state, and could then apply that to, again, these 10 subjects, 10 sessions, and we again see that this kurtosis is correlated with the extent of that sleep index. So how likely they were to be in a sleep state versus how likely they were to be in a wake state was related to that kurtosis measure. So it seems to be that arousal or likelihood of falling asleep is leading to changes in correlation that we can measure. Okay, so what can we say causes fluctuations in bold correlations? First of all, sampling variability. Stationary simulations generate nearly identical fluctuations and correlations as seen in real data. Artifacts, head motions, and changes in respiration cause artifactual non-stationarity. Externally imposed task states in cognitive state do cause changes in resting state correlation. These effects are significant, but they are modest as well. And then arousal changes. These are bona fide changes in states that are observable, and we can sort of link them back to external measures. What's not so clear is whether we can say that these are about moment-to-moment thoughts. I don't think that we have any way of giving evidence of something like that at this point, and I'm not sure that it would clearly make sense to do that in the case of resting state functional connectivity as a measure itself, as opposed to many other measures that might be more closely related to that kind of process. So it's not all bad. Stationarity does not preclude many interesting dynamic features, okay? Fluctuations may still be behaviorally relevant. You can have a stationary process. Here I'm using like a swinging pendulum. The statistics of the process do not change, but there may be some dependence on where you are in the swing in terms of a consequence in the world. And that could be a measurable observation. Also, I think a really interesting avenue of research that relates to this is the concept of lag correlations, which are also real dynamics that are not precluded by this observation of stationary multivariate Gaussian. And this is, I won't go all through the details, but this is about computing across different parts of the brain lag relationships that, and they may be stationary as well, but what's quite interesting is that these seem to be robust features of bold data. So they are stationary, but they actually are dynamic in the sense that you have lag relationships, and they are certainly not temporally invariant. And in fact, the multivariate autoregressive model that includes the lag cross covariance. So to be clear, the model that I talked about earlier, actually we're just enforcing the static correlation matrix and the autocorrelation within the power spectrum within each signal, but it doesn't include those cross-spectral data. But if you do include that with just to the first order, you actually get closer to the real data. And I think this is sort of a confirmatory evidence that these lagged correlations are in the data, and therefore the model that includes that kind of feature is closer to the real data for that reason. Okay, so be careful. Be very careful. Be sure to look at your data, worry about the artifacts that may be in it that can be contributing to all of this, and can maybe explaining a lot of differences that you see. Differences between patients and controls often can be counted in terms of how much they're moving their head, or other changes in signal to noise that may be specific to your patient population. And so a lot of certain differences may be well accounted for by things like that. Be sure that you compare to an appropriate null model that's well-defined so that you can explain what you are explaining with your observation that's not explained by a simpler description. And I think I had one other thing, but now I can't remember it. So, and also don't forget, going back to the original point, RFC networks are largely explained by common features across people and stable individual differences. That is the majority of the variability that you'll in the measurement of functional connectivity. And I think it's maybe as it should be. The brain must allow for adaptive plasticity while simultaneously maintaining its functional organization over extended periods of time. And we may need mechanisms that serve this latter function. And resting state functional connectivity may be more closely related to those than moment-to-moment cognition. So there's a possibility, as I said before, that we're talking about different mechanisms that are represented by different frequencies of bold content. And with that, I want to acknowledge everybody who is involved in this work over the years. There's a lot of people who've all been fantastic, on all the international collaborators as well. And thanks for your attention.